Okay, welcome back to this workshop. We already had 2 sessions. The first session was very basic about how to install R, what R is, and that everything in R is basically stored as a vector of something, vector of numbers or vector of text, and all the operations in R are actually vectorized. So if you add something, then you add something to each element of the vector and so forth. We had some exercises. In the second session, we talked about how R stores data, which was kind of boring. We went through all those data types. We started with vectors, which is the basic data type. Then we talked about matrices and that you probably need to use brackets to subset rows and columns. Then we went on to lists, which is a very basic, very important data type where you can store different types of data in one object. And finally, we ended up with data frames, right? And data frames is really where we wanted to get to, because this is kind of the basic data structure that you use in data science, which is basically a spreadsheet like you have in Excel that has columns, and each column has a different type of data in there, or it can have a different type of data in there. For example, it could be numbers or text and so forth. And so we ended up with this data frame idea. For us as the user, data frames kind of look like a matrix. You can subset rows and columns. The only difference is that if I get a row, the values in each position can be of a different data type. In a matrix, they would all be numbers or all be text. But conceptually, really fast, there's not much difference to a matrix. Only all those matrix operations that we know from algebra, they don't really work because you cannot multiply a spreadsheet with another spreadsheet. And it doesn't make sense because you have text in there and so forth, and that doesn't work. But just like handling it, it's the same. Okay. And then we, I think, talked about like importing Excel files and reading CSV files. The healthy choice is export whatever you have from the tool that you have as a comma-separated values file, and then import it in the other tool, for example, in Python or in R or whatever it is, import it from the comma-separated values file. Most tools that we have, most software is smart enough to look at the CSV file and figure out, oh, those are all numbers, so probably it should be numbers. This is all text, so it probably should be text. If you read directly from an Excel file, it's kind of tricky because the Excel format is not exactly open source. So people who write those readers kind of reverse engineer what Microsoft really wants to do. So what we saw is that it actually didn't read the data perfectly. It like made some numbers into text and we had to fix it. That wasn't really fun. Okay, then we ended up with functions, loops, and apply, which we wanted to finish, or I wanted to finish with you last time, but we didn't quite get all through it. And this is kind of like where we ended up with. We started with functions, with built-in functions like this random uniform function that gets a number here. And this just says, if you look at the help page and in RStudio, everybody knows how to get help in RStudio. Right, there's a little window. Let's actually go back there to remind you. If I open RStudio, I guess this is RStudio. Or this is not RStudio, or it doesn't open. Let's find RStudio. Oh, it's just really slow. This machine is way too slow. I clicked on it like 20 seconds ago. Okay, there's RStudio. Down here is your helper, right? And here you need to activate the help thing, and then you can write here. And I think I had runif for random uniformly distributed variables, and it tells you here in the usage how you can use it. And if you look at runif here, then the first argument is an n, and n is the number of observations that you want. And so if we go back to our slides.
Michael, can you share your screen so we can see on Zoom?
That's a good point.
Thank you.
Totally forgot that. So let's see, share here, screen. Okay, now you should be able to see hopefully where we are.
Yeah, that's great. Thank you.
Okay. So here, this first line says, X gets the value of RUniform 10. RUniform is a function that already is implemented in R. It gets those 10 random numbers. We can use it. There's a function called summary, where you get the typical statistics for your number, 5-number summary. There's functions for sorting, and there's hundreds of functions that you can use in R They're very similar to the things that you would use in Excel or in Python or in any other programming language, high-level programming language. And often you just know what you want to do, and then you just Google and say R and whatever you want to do, and probably you will get to a page where somebody says, oh, you need to use the word sort. Once you know how the keyword is called, then you can go back to R, like we were before. And now I have so many R studios open. And you can type it in here, for example, sort, and it will explain to you how sort works. Here you have X, and that's the object you want to sort, and then there's one argument called decreasing, and this is logical, and you can say I want it decreasing or increasing, and you can read all those. The most important part always in those manual pages are the examples, because you can just look at them and see how they really work. Often what I do is I look at the first line where it says what arguments do I have, and then I go all the way down to the examples and figure out, is there one example that already does something very similar to what I want to do? And then I copy this and work with this, this example and change it till it does what I do. And I hopefully do not break the code when I do that. Okay, so far so good. Those were the built-in functions. We're also allowed to define our own functions, and that's a little more tricky. But it's really not too difficult, because all you need to do is you need to use the keyword function, write in here the list of arguments that you want, and then write in those brackets here, in those curly brackets, the code that you want to do, and then assign it to a name. And then this name is of type function, and you can call this function with numbers, since R is vectorized completely, and it knows what to do with plus, also with vectors. It also works on vectors, and I think on the next slide you see it also works with matrices. All data structures that R knows and knows how to do addition with, it will work with those as well. You will probably not need to write too many functions, but some things, when we write our or make our reports, require you to put in something that is structured like a function. And it might be something really simple like adding two numbers, but you need to know the syntax that you have to say function, then define some arguments, and then do something like addition with those arguments. Just the structure is really, really important in R, because you use it for certain things. Okay, we went through this. And I think this is where we ended last time, right? Okay, let's look at conditions and loops. I don't really want to spend too much time here, because it's for people who had some programming language, it's exactly the same. It's the same control structures that we have in any programming language. If you didn't, it's really not a big deal, because lots of those loops, people who use R normally don't even use those loops, because everything is vectorized anyway. So if I want to do something to a whole vector, I don't have to like do an iteration that goes through each position, because I cannot just do it vectorized. Let's look at them really quickly. So there's an if statement, a conditional statement here. It says X, I give X the value 12, and then I check, is X more than 10? If it is true, then the first part is executed. Otherwise, this is what this else part is, the second part is executed. I guess since 12 is more than 10, it will execute the first part here. So it will print X is greater than 10 to the screen, and it really does this, and it ignores the second part, because that's only executed if I make, for example, X the value 8 or something like that. So that's pretty simple. If you need somewhere in your reports or whatever some condition, that's what you would do. You would write this with an if statement. Now the thing that's a little tricky in R, which is that we know that even X, although it has only one value, it's still a vector. So potentially X might have like 5 values, 10 values. And what does this if statement do if X has several values? We know what it does if you compare a vector with several values with a number. It will give you back a logical vector of the same length, and will say true whenever this position was more than 10, and false if it's not. But then if will get confused, because if gets now a couple trues, some falses in some order. What is it supposed to do? Is it supposed to execute the first line or the second one? And that is really a problem. I think in the latest version of R, it will give you a warning and say, this is really not good. If X is a vector, so it will basically check if X was a single value or a vector, and will give you hopefully some warning if it is not. And I think in the good old days, it just took the first value, ignored everything else silently, and those were bugs that you would never find in your code. Okay. But what we often want to do is, if we have a vector, we want to do things like we want to check if all x's are greater than 10. And there's just a function all, a function any that you can use. They're very convenient to check those things. You can also use logical operators, like the OR operator, which is a single pipe. If you had a different programming language, it probably was a double pipe. Otherwise, you had some bitwise operations. Here, the single pipe is element-wise, so it will compare the first elements with the second elements into a logical OR. And there's also this double pipe, and this is really made for the if statement. It will actually do OR to those, but it will only do it to the first element of each of those vectors, so that my if statement is guaranteed to get only one value. I don't know how useful it is, because it still basically just uses two values and ignores all the other ones. So I'm not quite sure how useful this double piped OR in R really is. The same thing is true with AND, then you use an ampersand symbol. Okay, loops. Loops look really almost identical like in most modern programming language. You use the keyword for, and then have some kind of counter for your loop, and it says, I want to count through the values 1 through 5. And then I have some code that does something with the I, so I guess it adds it up, it initializes it with 0. And when we do this, then X will have the sum of the values of the numbers 1 through 5, because I goes through 1 through 5. It's not really exciting, because I could also just like use the sum function and just sum up the values 1 through 5. And that would be the way to go. It would also be way faster. R can also go through lists, but then it gets tricky and it does all kinds of recycling, and I don't really want to go there. But keep in mind that the things that you go through in your loop could potentially be other things like a list, and then it goes through the individual elements of the list, and you can at home try to figure out why, and gives us as the result 7 and 8 here. Okay, other loops, while loops. Well, I think I used R now for 12 years. I have not used a while loop. I wrote some for loops. I never used a while loop, so I guess we can just like say this is maybe not for us. The reason why I never used while loops is because everything is vectorized anyway. All the things that you would do with a loop, like summing stuff up, there's a sum function, so there's really no need for those. Also, maybe keep in mind if you want to do like high performance computing with R, which some people want to do, the functions that you use in R are highly optimized. They go right away and execute some Fortran or C code. The code that you write in the loop is going to be evaluated every time it goes through the loop. So this is a factor like 100 slower than this implementation. So keep your fingers away from loops. They're really not good for you in R. They're also not good for you in Python. They're actually not good for you anywhere other than in C++, where it compiles it directly into machine code. So don't do loop if you don't have to. And for most things you don't, because you do basically almost everything with functions, or do some linear algebra, some matrix multiplications. Will do lots of adding, multiplying, and summing up at the same time for you, and they'll be more efficient. Okay. In addition to loops, R has a whole family of apply functions, where it applies a function to data. And the one that we already looked at when we talked about matrices was the apply function, where we can give apply here a matrix and then tell it we want to apply a function to this matrix, and we want to apply it here to the margin 1, and margin 1 is defined as the rows, and then we just give it a function. So this says take matrix M, and for each row apply the sum function, so sum up 1, 4, and 7, and this will be our first result. Then we sum up 2, 5, and 8, it will be our second result. So it gives us the row sums, and row sums is another function that is defined that really does this. We can also do it columns, or we can use our function here. So whenever you have a matrix, apply is good. For data frames, apply doesn't really work, because we know data frames don't have just numbers in there, they're mixed, so don't do that. Since we have lists in R, there is also a function for lists, and it's called lapply. And instead of rows and columns, it applies it to each element of the list. So for example, here, my list contains the sequence 1 through 3, then 6 and 7 through 3. So it has 3 elements. And then I can see I want to apply to my list a function. And I write here the function. That's why I told you before how to define a function. I said my function gets 1 element, and this X will be in my first run the first element of my list, then the second element of the list, and then the third element of the list. And I want to apply a function that I already knows, which is reverse. So it just reverses vectors. So if it gets a vector 1, 2, 3, it will reverse it, and that's why the answer that we get is 3, 2, 1. And it does it for each element, and you get back a list with 3 elements. Just the reverse function was applied to each of those elements. And lots of those things can be very, very helpful to do things very efficiently, because remember, data frames are actually lists of columns. So if you want to apply something to each column of a data frame, you could just say apply, give it a data frame, and say I want it, whatever it is, what you want to do with your columns in the data frame. If you want to use apply, but the result that you get is actually not something that you need to store in a list, because maybe I have a function that returns only one value for each list element, no matter how much it is. For example, the length function, we just look at it and say, oh, this has 3 elements, this is 1 element, this has, I don't know how many, 7, 6, 5, 4, 3, so that many elements. And then you want to simplify this into a vector. You don't want to have a list with 3 elements that each have only a single element. And then you can use sapply, which is basically a simplified list apply. So it applies something to a list, and if it can, it will simplify the result into a vector, and you get a vector that says the first element of my list was length 3, the second one is length 1, the last one is length 5. Okay, so far so good. There's some exercises for you to do at home again to kind of like practice this. And now we can actually go to plotting, and then we are done with all this like direct instruction that I will give you, and then we can actually look at some examples, and you can start writing your own code in here. Okay, so the last thing is plotting, and this is what we do in this section. What I'm going to teach you and show you is only the base R plot functions. There's packages that you can install and load, and they will make plotting way prettier, potentially way easier. I don't think that's really true, because it will make it a little more complicated, because you need to understand how those kind of plotting frameworks work. So we will do the base plot functions, and then we'll look at some interactive plottings when we look at our dashboards. Okay, simple plots. The first thing that we need to learn about plotting is that R plots things on devices. And so what is a device? I guess a printer would be a device, right? And usually if you print something, you print it on a printer, and there might be a laser printer and some other types of printer, color printer and so forth. So R separates it into devices. And whenever you see something on the screen or you save it as a file, it really plots it to this device. And the standard device on a Unix machine is called X11, and that's just the windowing system of Unix, and it just means it's a Unix window. Same thing on Linux. If you have a Mac machine, then Quartz is your Windows manager and your graphics engine, then it will make a device for your operating system and plot it there. If you have Windows, it will make a Windows window and plots it there. The reason why R does this differently is because it needs different code to display something on a Mac than on a Windows machine and on a Linux machine. Also, those devices work slightly differently. They have different capabilities. Most of them can make things like transparent, and most of them can do kind of like fancy things and use different fonts. Sometimes maybe you have realized that the fonts on a Mac might look slightly different than on a Windows machine, and if you have PDF files, then it might like use a different font and substitute it because it doesn't have the one that it needs. So this is why it has those devices. When you run R on a Windows machine, it will automatically start this Windows window. Let's now look at RStudio. And the tricky thing with RStudio is that when you go here to plots, this area to the right here is also a plotting device. And it's not this X11 or whatever the other plotting devices are, but it's one that ships with RStudio. RStudio has its own plotting device that it opens, and everything that we plot goes into this plotting device. It's kind of like a Java written plotting device. And whenever I say something like plot 1 through 10, it shows up here in this kind of plotting device. If I want to show it now in a different plotting device, I can open a plotting device. On this machine, I probably should say Windows, but I think X11 on all systems is linked that it will open the appropriate device for your machine. So it opens now this new plotting device. And if I now plot here and write the same thing and look back to this plotting device, then my result is now on this plotting device. Till I close this plotting device, and I can either close it here or I can write here. Can I make this stick? I don't know how to do this on Windows so that it doesn't go in the background. You can also write def.off for device off, and it will also close this plotting device. Okay, so far so good. So I guess, I wonder what happens if I open here a Mac device. It's called Quartz. It might just say maybe that it doesn't have that. Quartz. Oh, it says it doesn't. On your Mac, it will say, yes, that's fine. And I think here I can say Windows. And then it will open basically the same devices as before. And you can have as many devices open as you want. And if you're really smart with this, you can actually switch between devices, and you could make kind of like your monitor have like 15 different devices, and different things are shown on different devices. So that's pretty cool. Still a lot of work. It also has devices like PDF and PNG, and when you open them, then it will not display it on the screen, but it will write it to a file as a PDF or PNG. There's also a JPEG device. And if you want to know what devices there are, you can actually write in R here, RStudio, > devices. And it will give you a list of all the devices that your machine supports. So here we have Windows, PDF, PostScript, Xfig, Bitmap, Cairo PDF, I guess it can do those. And you can go down, there's lots of devices. And it will actually natively write those files and create them from, it knows how to create them from all your plot statements. You know, hopefully there's two different types of ways to plot. Some of them are pixel oriented, like PNG and JPEG, and some are vector oriented, like a PDF. So if you plot something and you want it to look really nice, then you need to use a vector oriented one, where each line is really represented as a line, not just a bunch of pixels. You probably have seen like a Word document that somebody sent you, and if you like zoom in, the figures don't look great. They're all pixelized. Then that means they didn't use a vectorized device. Okay, let's go back to our devices. So we will talk here about some high-level and low-level plotting functions, just the basics of base graphics. Very popular is ggplot, and if you want to learn about ggplot, it takes a little bit to figure out how that really works, because it has a grammar of graphics behind that basically builds up images by having different layers layered on top of each other. But there's whole books and like tutorials that you can look through, and also videos. I think I have a link on the website as well, where somebody explains to you how it works, and then you can use those as well. It makes very pretty visualizations. Now, high-level plotting functions, the base function is called plot. And I create here vector x with the values 1 through 100, and a vector y, which just takes x squared, and I plot x and y, and I get a standard plot here with little circles used as my markers, and it has here x, and then it has the squared of x on my y-axis. It's pretty straightforward. I can also change the way that it looks a little bit. I can say here, I want to have plot x and y. The type, how I want to plot it, is supposed to be a line. That's what L stands for. The line width is supposed to be 3, so it's slightly thicker. And the color that I want my line is red, so that's why it's red. And then I want to add a low-level function here. I want to add an AB line at the vertical position 50, and the line type, LTY line type, there's lots of abbreviations, unfortunately, here, is supposed to be 2. Line type 1 is a solid line, line type 2 is a broken line, and it's supposed to be at the vertical position 50, so that's just another way to say that it's on the X position 50. I want a vertical line in here. You can use this to mark something in your plot, for example, if something happens to the right or to the left, and so forth. So plots are created by using a high-level plotting function. Then you kind of like put more information in there. There's functions to make arrows and all kinds of things, and text that you can place in your plot. Okay, now let's go through how you find help for that. So question mark plot would give you help. You can also just go here. Instead of question mark, you just write plot in your help window, and it says here it's a generic XY plotting function, and it says that for simple scatter plots, it actually uses plots default, because here it actually says not much about it. If you click on plot default, you will see it has lots of arguments. It has limits for X, limits for Y. You can make things logarithmic. It has a main title. It has a whole bunch of them, and then it has those dots, and in R dots mean there's a whole list of other parameters that you can add, and it will use them if it knows what to do with them. Okay, so this is my plot function, and plot default is the regular function that we use. It also has plot dot with some other object types, and it will then use those functions. An important thing is graphical parameters are stored in R kind of in a weird way. Sometimes you kind of want to make some sort of like design choices and say all my lines have to be pink because I really like pink. And you want to say once, make every line pink, and then whatever I plot, it's supposed to have pink lines. And this is done with this parameter argument here. You can actually set global, well, parameters for the device, and then whatever you do with this device, it will follow those parameters. And most of those dot, dot, dot things in the plots that I showed you before, if I go back here, this dot, dot, dot actually goes to those parameters. So you can change those parameters there as well. You can also look what parameters you have. If you say here PAR, then it will tell you this is to set and query graphical parameters. And if you go through, it's just like a super long list of what it can do with how big things are and how much scaling you want. And if it's like landscape or whatsoever, there's lots of things. And the way to find something here is to go to this find in topic and say, I'm interested in doing something with margins. And then you write just margin and then go through and try to figure out where it talks about margins. As here, there's something called my, even has a little picture, and you can change margins if that's what you want to do. Okay, so far so good. Let's now look at a few examples. Simple scatterplot. The first thing that I do here is I load the data set from the website that we used last time. Remember, there was this Major League Baseball data set that's stored on the website where this course lives, and in the directory data science workshop examples, and it's called MLB cleaned.csv, and read.csv allows you to actually put in a URL and it will download the file and read it as a data frame. And the data frame had columns height.inches dot, and this happened because it was an Excel file. It had too many spaces and R converted them into dots. And weight. And what I do here is a plot that plots the height of players versus the weight of players. And you get this scatter plot here. Each dot is a player, and you have the height as my x-axis, weight as my y-axis, and we kind of see that there's some correlation between weight and height, right? Taller people are heavier. That's kind of like not really too hard to imagine. And there's kind of like a little bit of a cloud here, saying that there's some mixture. There's some people that are slightly higher, but they might actually not be as heavy as other people. And the reason for baseball could be that they do different things, right? I think we looked at it last time a little bit, that there's people who run a lot and they probably are not as heavy as the people that stand around a lot or need to be very powerful throwing stuff. So this is in our data here. Also, what I do is I give my X labels and Y labels here, nicer labels. So I say here height. So this height from up here goes down here. And the main title is weight by height. So it creates this plot. If I use, instead of vectors for X and Y, my whole data frame, then interestingly, plot does something different. It represents the whole data frame, or it tries to represent the whole data frame in a visualization that can present more than just two variables. And this representation is a scatterplot matrix here. So for example, I get the iris data set. Did we look at this last time before? Like those are those 150 iris flowers, and what I have is 4 variables with different measurements. And if I look at the first 4 columns here and I get rid of the 5th, remember you can index with a negative sign to like get rid of something. So if I get rid of column 5, which is text, and kind of like making a plot with text is not really great. And I give this to my plot function, then it will make this kind of like array of plots, and it will plot each variable against each other variable, and then you can identify and say, oh, there's a strong correlation here. This one group here is kind of far away from the other group. And that works well if you have very few variables. You can imagine if you have 50 variables, all those plots will become very small, and the usefulness is kind of not a lot. This plot is called a Bayes plot, and the plot function for data frames will automatically resort to this Bayes plot. And the reason is because plot is generic and it looks at the data type, and depending on what you give it, it will try to represent it in the right way. And I use here as the color the 5th column here. That's why the different species or subspecies in here are colored differently. You can play with that. Often it does what you want right away, and sometimes you have to kind of force R a little bit to do this. Next thing that's important, bar plots. Bar charts, I think, are very, very important. Lots of our business data is represented as tons of bar charts, right? And then if we get too tired, we make a couple pie charts in between. So I make here my own data. I make a vector that has the first element. I give it the name Sandra is 3.8, and I think this is GPA data. Michael, of course, gets a 4.0. And Peter, we don't know. He's probably a new student. We have no GPA for Peter. Then I sort this whole thing here, and I put it in a barplot function, and I get those bar plots. We see Peter doesn't have a bar at all because it's an unknown value. And then we have Sandra and Michael. Since there's not much data, those bars are a little bit kind of chunky and big. And you can do this, change this. If you say question mark bar plot, you will see you can make the space larger, and there's all kinds of parameters that you can make it prettier. You can change colors and so forth. Now with our basketball data set, I wanted to look at how many players do the Texas Rangers in this data set have for each position. And there's like 8 or 9 different positions in baseball. I assume that Tex is the abbreviation for the Texas Rangers. I wasn't sure, didn't have time to check it out, but I guess the team TX is probably, is there another team in Texas that could have that?
Yeah, sure.
Yeah, so, but they are probably AST or something else, right? So Texas is probably TX is probably the Texas Rangers. So what I do here is I select only the rows that belong to the Texas Rangers. Remember, if we have a matrix and we select something, then we need to give it row indices, comma, column indices. As my column indices, it's a little small here. I didn't give it anything, which means I select all the columns. But here I select only the rows where the team has exacted the value of text. So then my MLB underscore text has only those rows. And then I want to plot this as a bar plot, similar as before. But in order to do this, I need to do some calculations. I need to count. And the function R that does counting is table. It makes actually a tabulation. It basically looks at the variable, looks at the values of the variable, and counts how often is each of the values in this variable. And the variable that I have here is MLB Texas position, and table will just look at what positions are in there. It's all text, and then count for each positions how many you have, and gives you back a vector with the name of the position and the count. Very convenient. Also, I want to sort it from highest to lowest, so I put my table here into a sort function, and I want to say decreasing is true, so it goes from highest to lowest, and then I give everything to a bar plot, and I get this kind of like bar plot. I can stuff this all into a single line, so that's great. The only thing bad about this type of bar plot in R is that it doesn't have enough space down here. By default, it has the labels actually horizontal, and the labels are so long that they will run into each other, and it's going to look messy. It ends up not showing all the labels because it figures out it doesn't have enough space for that. So what I wanted to do is I wanted to put them kind of like sideways. And there's a bar argument called LAS, and I forgot what the short that stands, some arrangement, label arrangement, something, I guess. And if you set this to 2, then it will take the labels and put them sideways, like I have them here. But if I do this, it will cut off stuff. And let's actually do this. Let me download this, if I can, this data set. Where was it here? Copy and paste this, if I can. Okay, I also copy something that I don't want, I guess, but I can fix that. Okay, MLB. So it downloads MLB now from the website, and I see here that it is in my data set. It's in R here in this environment. And then the next thing that I had was selecting Texas and making this whole chart. Let's take this. Doesn't let me select just the code. That's annoying. So bar chart show how many. So this is the first thing that I want here. And let's get rid of this. So I select MLB Texas, and we see MLB had 1,034 observations, and MLB_Dex has only 35, and I can actually look at it. And then we'll hopefully see somewhere that the team now has only TEX in there. My original team, if I look at this, my original data set had all kinds of other teams in here. Okay, so it looks good. Now we can go back to the plotting here. Oh, this is annoying. Maybe if I click, if I click it a couple times, it might work. Okay. And let's just do it the standard way it comes. And this is a little disappointing. You see how the labels down here, there's only a few. If I open this and zoom and give it enough space, maybe it will eventually give us more labels, but it still doesn't have enough space. So I could play with it. There's one function called, or one parameter called CEX, which is the character expansion factor. And I can make this 0.5, hopefully, or I can't. Oh, it's called here, I guess, axis. Oh, that it makes this here smaller. So that's not good. You can always push tab to find out what you can have. So names, maybe that's what it is. I guess that's what it is. And then if I zoom, then maybe it has all the labels because it's enough space. But on the other hand, it's not great because it's so small. So that's not a good solution. So what I did is I used instead here, LAS is 2. And then it puts it sideways. But you see how it's cut off down here. So that's not great. And the reason is because this is called the margin. The margin is not large enough to put all these names, labels in there. So what I had to do was I had to actually change the margin here. And this is what the other lines here do. This line here, let me copy it. Changes the margin. What it says, change the parameters, change the argument margin, MAR, and it's actually the margin in rows, and it changes it, use in the bottom enough space for 10 rows, left 4 rows, top 4 rows, and to the right 1 row. And you have to look at the help page, and it will give you a picture and show you where you change your margin. So if I do this, and then plot my bar plot, then you see it will make a large margin down here, and it kind of like fits in there. Okay, so this is kind of messy, and that's just the reason why it is so messy is because this is kind of like old R/S code, and way to do it's not very user-friendly. So if you use ggplot, it will take care of that. It will actually look at the labels and make enough space and automatically do this. One important thing is if you change your parameters for the plotting device, you should reset them at the end. Because if you don't, then every plot that you will do in the future will have this changed margin, and that's not really cool. So what you usually do is here you say bar, old bar, and old bar is what I got here back from my changing my parameters, and you just put this line there and it will reset it to the original settings. Okay, histograms. Well, if you want a histogram, pretty easy. You say hist, give it a variable, and you can say with breaks how many buckets you have. If you don't say breaks, it will automatically try to figure it out. You can also estimate some density and overplot this red line as density. Really not too exciting. You can just do this. You can also do some images. Here, this is volcano data and images. I think this is elevations of some, what is it? Manga Wow in Hawaii somewhere. So if you have data like this, you can create images very straightforward. You can also change the color scheme. It has this kind of heat colors normally, but you can make it gray and all kinds of things. Okay, I don't want to go too much into details because you can actually look up nice plots for our own websites, and they usually give you the code and say, if you want to plot it like this, this is the 5 lines of code that you will need. Typical things that you can do with plot functions is you can use put an add argument there. If you want to add something to another plot, you can remove the axis. Sometimes you don't want the axis or make them manually, then you can say axis is false. You can plot x and y axis in a logarithmic scale. You can change lines and points. You can give your axis labels. You can give your figure a title or a subtitle. You find all of those when you say question mark plot.default. It will show you which ones it has. Low levels, once you made a plot, you can add additional points, you can add additional lines, you can add text wherever you want it, you can add lines with this AB line, you can add complete polygons on your plot if you want to, for example, put some annotation somewhere. You can put a legend there. This is quite useful, but that's tricky, so you will have to play with that. And you can add a title or an axis if you didn't already have them in your plot, and can assemble your complete plot with different pieces. The graphical parameters. For example, here I set my color to blue, my BCH, which is super awkward for plotting character, which is the symbol that you get if you plot a dot. I set it to 4, and 4 is an X, a little X symbol. And CEX, I make the expansion factor 2, so a little bit larger. And then whenever I plot something, I will get it plotted with blue, with this weird plotting symbol, and a little bit larger. And if I say X is false, then I can make my own axis. I can say X1, X is 1 here, then it adds an axis for the X-axis, X is 2, it adds an axis for the second one. And here down here, danger, whenever you change your plotting parameters, make sure that you reset them at the end. Or whatever you plot on the same device before you close it again will have those kind of like things in there. Okay, there's a whole bunch of things you can do. Plotting characters, you can change line types. If you're really interested in what plotting characters are has, a simple thing would be to just like plot 1 to, let's say, 50, and then say the plotting character gets also 1 through 50. And then there's not much space, but maybe if I zoom it, then it looks like this. And now you see plotting character 1 is a circle, plotting character 2 is a triangle, plotting character 4 is a plus sign, then an X, and you see it has all those plotting characters. And whenever you want to plot just with one plotting character, then for example, you could say plot everything with 20, then you have your plot with everything has this one symbol. I think you could do the same thing probably with the line type and see that it has like a solid line, a broken line, like one that's dash dot dash, larger dashes, smaller dashes, and all kinds of things that you might want to use for plotting. Okay, we used MAR, and MAI is a very similar thing if you need to increase the margins, and you can also put multiple plots on one device by telling the device, please make space for 4 plots, and it will plot them one next to the other one using this MF call and MF row. Healthy thing here, Google multiple plots are, and just copy the code, whatever they give you, and do that. If you want to save your plot in a file because you want to open it, for example, edit to a Word document, then you can just say, I want to create a PNG, give it a file name, you plot something, you say device off, and you will find a plot in your working directory, a file that has this plot as a PNG in there. Does anybody know, can Word incorporate PDF files as plots, or do they have to be JPEGs or PNGs or something else? I'm not sure, maybe now it can. In the good old days it couldn't, which was a pity because PNGs and JPEGs are like those pixelized versions, and a PDF, if you ever try to like make it large, you see that those lines always look crisp, the points look crisp because it's vector oriented. Okay, and there's JPEG, TIFF, and all kinds of weird formats that you might want to use. Okay. Other plotting paradigms in R is there's a whole package, a group called grid that uses a different way to create graphs. And there's ggplot2, and that's probably the most popular way to plot things. And ggplot is not just on R, Python also can do it, and other tools also can use this idea of creating graphs in that way. If you're interested in creating graphs, then let me go back here. Then there's a link, this R graph gallery, and you can open it. And then takes a while. Then there's a whole bunch of images, and it will tell you right away, right next to it, how to create this image. For example, this interactive plot with like different bubbles, they give you really the code here. Or if you go down here, if you want something that looks like this, you can actually click see code, and it will show you the code to do this. And I think it's even organized by different types of plots. If I find out here, chart types, can say, for example, I really want to do something that looks like this. So you click on it, They're called rich line charts, and it will give you all kinds of examples. You click on it, it will give you code, and you can just put your data in and make those visualizations. That's quite easy nowadays. And you see those things are not just for R, they also work with Python and JavaScript and all kinds of things. Those libraries usually work with all of those. Okay. Last thing here about plotting we're already done is again some exercises where you can make some plots and change some things just to practice this. Okay, so far so good. That's great. We're done with our kind of like boring slide sets, but unfortunately there's so much that we needed to like cram into our brains and see that I had to do it this way. And now we can go back to creating something. And here under exercises, in session 3, the first thing that I want to do is I want you to show, and actually I want you to create a report in R. With the idea that you have a data set, you have some code, the data set maybe changes every month. Every month somebody emails you a new data set, and you are supposed to create a report. And there's lots of reporting tools that SMU, for example, also uses. I think it uses Cognos or something, IBM tool to create reports. R can do reports as well, and the report that I want to create should look kind of like this. Here, this is my R Markdown example, and what this report does is it loads the MLB data set that we had before with the same code as before, and then does some analysis, very low-key analysis. It inspects them first, it gives me the first few rows of my data set. Then I want to show it in a little bit of a prettier version where the table is not just like raw R output, but it's formatted like a table. And there's a package called knitter and cable, which makes a knitted table. And then it looks like this. We can also make an interactive table in our document. Since it's an HTML document, you can actually here say, I want text, and it will automatically go down here. You can also go forwards and backwards. So you can have an interactive report. If you share it with somebody as an HTML file, they can do this. I want to do some data summary, and you can just like take the summary and do it. I might want to add some charts here. For example, here a histogram for the size. You can also have some more interactivity in here. And then I have here down here an exercise. So I want you to now show you how to kind of like start something like this. Let's go to RStudio and go to File on top and say New File, and then you have lots of choices. What we did so far was we started an R script, right? That's the first thing that you should do anyway, and it will create a new file here, and you can put in R commands and execute them with this like little run button and so forth. But what we now want to do is we want to do R Markdown. This is the third down, and if my computer was a little faster, it wouldn't take so long. Let's see if it can do it. And then it says document requires updates. Oh, since I never did it on this machine, it needs to update a few libraries to be able to do R Markdown. A lot of libraries, let's see. And here we have it. And I give it here a title, and you have a choice. You can make a document, a presentation, or Shiny, or from template. Right now, we want to create a dynamic document. So I call it MLB analysis, and it's made by me. And then you can say, do I want to render my document when it's created as HTML, PDF, or as a Word document? Let's leave it as HTML right now, and then we can later on change it to the other formats. Then you say OK, and what you get is you get kind of like a first shell of a document. It already has filled out here. This is called the header. It has filled out that the title is supposed to be MLB or MBL, what is called Major League Baseball, MLB analysis. The author is Michael. It gives it a date and says the output is HTML document. And then it uses markup to, or actually Markdown to create those documents. And I printed out for you some Markdown documentation for people who are online. If you go back here to the website and look at learning material here, if you look at Markdown cheat sheets, it will open for you the cheat sheet that we're going to use here in the class. And it's full of very useful information that tells you how to use Markdown. And the whole point of Markdown is to kind of be able to format documents similar to Word documents, but using just text characters. So don't use like highlighting something and making it bold, but just like writing down, I want it bold. And for example, here, if you do those 2 number signs, then this means this is a level 2 header. And in Windows, you probably would have to go there and go to like formatting somewhere and say, this is supposed to be a level 2 header. So this says here, our Markdown is supposed to be a header. If you put in a URL, you just put it in those like pointy things and it will know it's a URL and will link it. If you want to make something bold, you put it, for example, here in 2 like stars at the front, and at the end it will format this as bold. And if you want to include dynamic R code, this is what you do. You put a block in there that has 3 quotation marks, and the reason why they use 3 is because lots of people use 2 for like quoting stuff like text. So they use 3 quotation marks, and then in brackets, the minimum that you need is this. You need to tell it what kind of code you have, because Markdown is not just for R, it's also for Python and all kinds of other things. And you have to tell it the code that's in this block is R code. And the code that they have in here is they use the dataset cars, and that comes standard with R, so they don't even need to load it in. And they say, give me the summary of R. And you can then see here things. You can, for example, also execute this one block here, and you will see this is how it's going to look in the final document. And it puts it automatically right in the document. Here we have another section header, and then it says here plot pressure. There's other things that you can add here. You can say that you don't want the document actually to contain this code. It's just supposed to contain the plot. And I think those are all the examples that we have here. So up here now, there is this knit button with this little yarn thingy and needles. And it's supposed to take the code and knit it together with the document to create the final document. If you click down here, it says you can knit it to HTML, PDF, or Word. And by default, we set it to HTML. So if I knit this, it says it wants to write my document somewhere. And I say, I guess, save. Do I need a file name? Oh, on Windows, I need a file name. Oh, I never gave it a file name. Maybe that's what it is. Let's first save the file on my desktop. And let's call it mld.rmd. That's the standard extension for R Markdown documents. So I save it, and then I knit it. Now it should like do it, hopefully, without complaining. And it does it, and it creates now this dynamic document. There's this URL in here. Those are headers. You can also up here say that you want a table of contents and all kinds of things. So it does very similar things that Word does. You can also have a reference list, and it will link them automatically together. If you ever wrote something for Wikipedia, that's also Markdown. It's exactly the same kind of syntax. If you wrote something for certain blogs that you use Markdown, it's the same kind of structure. And you see, it puts the input block code here, and then it puts the result of the R code in here, and also embeds the images. Let's now try to make this into a PDF file. Let's do this, knit to PDF. And it does something, and hopefully it works. And then it says it cannot do it because on Windows PDF LaTeX is not installed. That's a bummer. You probably need to install this yourself. Does it say something here? If you're not sure, you may install Tiny. Oh, maybe we can do this. If we are not sure, install TinyTech. Let's do that. If we're allowed to do this on this machine, I'm not sure. Next, you will see an error box. This will take a few minutes, I hope not. Okay, then maybe while it does this, we can talk about the what Markdown does, the cheat sheet that I gave you, or not on this computer. Did I kill it? No. Oh, there it is. The way that those Markdown things work is described here at the left side. It takes those RMD files, that's where we have text with Markdown and R commands in there. In this RMD file, then it will create an intermediate layer called pandoc, and then it will use this pandoc document to create a Word document or whatever the output format is that you want. The idea that they had initially was that we want to create lots of different file formats out of our documents, and it's really stupid to like write something in Word. If you did research and wrote your thesis in Word, and then your advisor said no, it has to be LaTeX, then you probably had an issue because it takes a long time. And so pandoc was supposed to kind of like remove this problem, because you write it then in one of the 5 different input languages. It has a translator that translates into pandoc, and then from pandoc you can translate it into Word, LaTeX, HTML, whatever you want as the output format. The downside is though that it has only, it's not as fully featured as if you would write something directly in Word, where you have total control over how the output looks like. But it's still very, very powerful. And let's now see if R is done, or it's still installing stuff here. I wonder if it gets upset if I try to knit it now into Word at the same time. Okay. It's still running. Oh, they really need a new computer here.
How do you spell LaTeX? What were you calling it?
Yes, LaTeX.
Oh, LaTeX.
Yes. That's the way most textbooks and books are written that have lots of math in there, because typesetting math is really easy in LaTeX. In Word now, it's almost as easy as in LaTeX, because Word figured out we should do it the same way as they do it in LaTeX, and you can now kind of type it very similarly. Oh, it finished it. It made a Word document out of this thing. It said R Markdown, and I think it hopefully formatted this as headers and things like that. Has the R code in here, was able to put in the figure and so forth. So you could at least, if you want to make it in a pretty Word document, now edit this, but you already have kind of like a basis to start with those documents. Okay, let's now go back to, I don't know if the PDF installation is done. Oh, I think TinyText is probably done. Or is it still? No, it's still doing something. So at least in theory, you can make a PDF file, but you can also save it as a Word file and then make it into a PDF file afterwards if you want to. If you have interactive elements, then you need to make it into an HTML file, because obviously a PDF can do some interactivity, but mostly not really, and a Word document is not interactive at all, right? It's like it doesn't have anything with shifters and things of that nature in there. Okay, let's now look what I did when I when I made this file that did that was for the MLP. Let me save this, save link as on my desktop, and then I will open it from there. File open. I guess this is what it is here. And it wants some more things. So what I did is I did exactly what I showed you before. I went to File, New, and made a new Markdown, and then I started editing this. I basically removed the code that was already in there and wrote my own code and left some in here. So I said loading the MLB dataset, and I made an R block that has exactly the R code that we had before that loads the dataset as a data frame into memory. Then I said I want to inspect it with our raw output. We know the head function takes the data frame and shows us the first few lines to kind of see what first few rows, see what's in there. There's the fancy option, and the fancy option is by just taking this head and wrapping it into this call that's called knitter cable. And I'm not sure if that is on the cheat sheet that I gave you. Yes, it's on the cheat sheet. If you look at it down here, when it says rendering things, let's see, this is on page 2. It's on page 2 here. Rendering something as tables. It looks different. Where is this? Here. Here it says you can render this a table with knitter : cable, and that's really what I did. And it's this first example that you see here. You can also use other packages that make it look prettier or different if you want to. I use this version here. And so I just wrapped the header in this table. And then data table is an interactive package that makes actually HTML tables that are interactive. Let's look at this in the way that what I showed you here, that you get this table where you can actually go through the table. You could also see I want to show maybe 25 results, and the table becomes longer, and you can also sort them by age, by weight. So it's kind of like almost some interactive dashboard that you can have when you just want to look at the data frame. And that all doesn't render on Windows, on Word. That only renders on HTML. Okay, let's go back here. What else did I do for data summary? I just made summary and also wrapped it into cable so it doesn't look like just R code. Then I made my histogram, and then I used the Plotly version of a histogram, which is kind of like a little harder to write. But Plotly is another package that allows you to make those interactive charts. And the way that this interactive chart looks like is, if we go down here to where the Plotly result is, it looks like this. It has those kind of buttons. You can zoom into certain areas. I guess you can probably somewhere here reset it again. Probably this resets it. You can make screenshots and save it as a PNG and so forth. And you can do all kinds of other things, and it also shows you something interactively. Plotly can make interactive scatter plots, interactive all kinds of plots. And if you want to know what Plotly can do, you can go to the website, and I probably have here a link. You can just go on Plotly, and it will show you different examples. And if you say you want something that looks like this, I guess you just like probably click on it, and it will give you a code and a tutorial on how to make your figures really fancy and interactive. Was really not hard to do. It took me like 20 minutes to throw all this stuff together, but I already knew what packages I wanted to use, data table and Plotly, so that was easier. But I put the links here. Okay, what I want to do, let's see how much time we have. We have probably like 10 minutes or so left. Let's first go through the dashboard, and then I show you what the exercise is that you should be thinking of. You can also, instead of this exercise, take a data set that we have for work and make a report that may be even useful, or at least a start for what you want to do with your data. Okay, let's go to this dashboard, which is like this. And our dashboard that has here 3 panels. It has this interactive table where you can filter and sort and go through them and so forth. Then it has an age distribution as this interactive plot, and the scatter plot that we had before, but also done with Plotly, so you can zoom into different things and so forth. And it has all kinds of weird stuff. And it shows you also, if you go over dot, who this person is that has this weight and height. So this is a semi-interactive dashboard. If it was fully interactive, then you could, for example, say here Texas, and it would only use the data for Texas here. Right now it doesn't. It has 3 very totally independent panes. This is always all the data. If you want to make it more interactive, you actually need to use something that's called Shiny, which lets you put in code that tells it how to link those plots together. For lots of applications, it's okay already to have just this, to like always have the same kind of like 5 plots that you want in there. And whenever the data is updated, you just reload this page. It will load the new data, because every time I reload it, it really loads the data set, and it really does all the analysis, and then it plots it here. Okay, let's look at how this dashboard looks like. And I like this dashboard because you can create it using RStudio by just going to File, New File. I think it's also R Markdown from template. And, oh, that's not it. Where was it? File, New File. It was, oh, I have to install the package first. Tools, install package. And it's called, how is it called? It's called Flex Dashboard. Flex Dashboard. Here, we install it. Hopefully this doesn't take too long. Okay, it's done. And now maybe we can do this. New file, Markdown from template. And now it has Flex Dashboard in there because I installed it, and I can say okay. And it will give you, similar like the other one, a half empty or half filled dashboard. You can save it. Right now it has actually nothing in there. And so what I did is I used this and filled it out with some code and ended up with this dashboard. Save link as, desktop, save, and then I open it in RStudio. Dashboard, this is it. And so I filled this out here. I put some startup code in here that just reads my MLB dataset, same code as before. And I say here include false, which means that it doesn't show this on my dashboard because I don't want to really code on my dashboard. I want just the results. And then I make my first element and I say I want just a data table with MLB in there. My second one has this plotly histogram in there. I just copied and pasted it from the other document that I made. And the last one I also made with plotly a scatterplot, and the syntax is kind of weird. You have to do it this way. This is the X values, the Y values. Don't really ask me why you need those little baby lines, but the plotly people like baby lines here. And then as text, I want to put the first name, the last name, and the team in there. And that's actually the whole dashboard. It's literally reading the data set, making a table and 2 graphs directly from the data set. And if I run this with init, it will create an HTML file that has all the results. You can take the HTML file, email it to somebody. They can open it in their web browser, and it's going to be hopefully not as slow on their machine as it is on mine. And if you open this up, they will see exactly this kind of thing. So it's a good idea to share data this way, because then they can kind of like look through the data. And if you have some more fancy code in there, you can make some really pretty cool things with very little effort. Very little effort under quotation marks, right? Because you still need to be able to find our code and put it in there. Putting it in there, I guess, is not so hard, but to make all those plots really plot them in the way that you want them can be tricky. But most of the things you can find somewhere and like just plug in, and you have then a different panel here. The panel structure is really simple because the panel structure is just, you see, I want a column that's 650 points wide, and the name of the panel is just like a header, and you can just adapt those, add more panels, whatever you want in your dashboard. Okay, let's go back to this thing here. So what you're supposed to be doing in your ample spare time is to either go through those exercises that I have here, which is analyzing an individual team. This is just the data for all of the teams, but you can choose one team and like answer questions like, and write it as a report. This team has so many players. This team has, I don't know how many, what is one of the groups, like the people that hit the ball hitters, people. The average age of their, oh, they don't have quarterbacks, right? They have other people, is something, what's the youngest player, what's the oldest player, have some ideas of what the analysis could be here. Or you can read through this and say, no, I have a data set, I want to load it, and I want to make a dashboard and a report about my own data set. And then we can talk about this at the beginning of the next session, where we will talk more about predictive modeling. So we will at least do some linear model and then some decision tree and something similar, and maybe stick it into a dashboard or stick it into a report to show the data. Okay, that's it for today.
What is the exercise? Is that on your?
This exercise, if you look at session 3 under exercises here, the first thing, you go to this MLB document. This is the automatic document that I did. And you start with this RMD file, right? You can download it and then you can start editing it, deleting stuff that you don't want, adding more sections, and so forth.